talk about the way I think what we're all doing is radically changing the way that we design and make things. And, the whole conference is about hardware and software. And the real question for me is not that this is happening, but it's why now? Why all of a sudden is this happening now? And a lot of it to me seems like it's this combination of really taking microprocessors and software and applying it to almost everything around us. And so what's going on is hardware is changing dramatically, software, but it's also our access to funding, it's our access to information, the way we are self-organizing, the way we meet up with people and find information and form teams and make new things. That's what's changing. So what I really wanted to do this morning is focus on two things. I wanted to talk about how the hardware is changing, and then I want to talk about how software is changing. So let me start with the hardware. And I think this is a useful distinction to make. It's four categories that I think about when I look at how the hardware is changing. So one is about additive manufacturing, one is subtractive manufacturing, the other is robotic assembly, and the last is nano-bio and what that means for how we make stuff. And while the categories are useful, the truth is, as you'll see, the lines are really blurring between all of them, and I believe they will continue to blur. So, starting with additive manufacturing, let me just start out by saying this is not what I mean by 3D printing. This is not what I'm interested in when it comes to 3D printing. What I'm interested in is machines like this. Machines that print metals, machines that print ceramics, and in general, if you think about it, I think much of what's been said about consumer 3D printing is way overhyped. And I think in the long run, if we look, the value that will be there is in the industrial use of 3D printing. That's where it's really going to make a difference. And I think the industrial uses of 3D printing have been way underappreciated up until now. So let me just think about 3D printing in general. And there are a few things I just want to kind of outline about what I see with 3D printing. The first one, and the absolute coolest thing about 3D printing, is that shape complexity is free. It's kind of unbelievable. I can design anything I want on the computer, and with little to no skill, I hit the print button, and the right thing comes out. And my 3D printer couldn't care less if it's the most complex object in the world, the most intricate design, or it's just a cube. It doesn't matter. And so that's the thing that keeps me going forward with 3D printing and excited, is that shape complexity with relatively little skill and your ability to make it. But there are a couple things that stand in the way of 3D printing that I think are fundamental to understanding how 3D printing is going to advance. The first one is the scalability of 3D printing. And the issue comes up that making 3D prints larger grows at the third power. It's a cube function. And so what I mean by that is if you're going to print something that, let's imagine you're going to print a cube and it's 1 inch on a side. And let's say it will take an hour to do that. If you want a cube that's twice as big, it doesn't take twice as long, it takes 8 times as long. And if you want one that's twice as big as that again, it's going to take 64 hours. So what you've done, if something took an hour to print and you want it 4 times bigger, it now takes nearly 3 days. So we need to understand that that's one of the fundamental things. The other fundamental thing is, I think many people have thought that something like Moore's Law applies to 3D printing. And despite the fact that my 3D printer has microprocessors in it, Moore's Law doesn't apply. And so what I think we're going to see as 3D printing advances is a very different trajectory than the one we're used to with computers and software. Moore's Law has been incredibly predictable. It's been predictive. And so as someone who writes software, in some crazy way, we could stand still, do nothing, and next year, our software was twice as fast. We will not have that advantage when it comes to 3D printing. We will need to experiment and explore and invent and discover and come up with new ideas. And so I think the improvements in 3D printing will be dramatic, but the path on which they improve is going to be completely different. The trajectory will look very different than what we're used to in the world of traditional hardware and software. So let me look at a few of these things. Here's an interesting new 3D printer. Many of you may have seen it. It's from a startup in Boston. It's called Markforged. And what they're doing is 3D printing carbon fiber impregnated in resin. So it's plastic with carbon fiber, printing single filaments of carbon fiber, making much lighter, much stronger, much more durable parts. Really interesting development. Here's another one that I think is interesting. This is from an artist in Amsterdam. His name is Joris Larman, and what he's doing is 3D printing metal. So on your, it was on your left and right, but here you can see it again. He's MIG welding with a robotic arm. Here's a sped up version of actually making forms in space by just welding it. I think it's a very cool, and like you see, it's a combination. It's part robotic, it's 3D printing, and you're making metal in space, computer driven. Here's another example. This is I think, a great example. And this is a combination, and this is probably one of the most interesting things I've seen in the last couple of years, is this combination of additive and subtractive. So you saw deposition of metal, laser deposition of metal, and then a machine that switches heads and goes from using a laser to deposit the metal to one that takes a cutting head and will now mill it like a traditional CNC machine. So really interesting combination here of going back and forth between the two. And I think it's one of the most astounding developments. As I go through my talk and I show you some of the things, I'll come back to this, because I think many of the things we're going to be able to design will only be able to be manufactured like this. By the way, I watch that all day long. My kids have come to me over and over again and said, "Dad, will you stop watching that CNC porn?" I think this stuff's incredible and really exciting. Here's some other work. This is Robotic Assembly. It's done by a team at the University of Stuttgart. It's Achim Menges. And what they're doing is robotic assembly of carbon fiber structures. So what they're doing is a wet layup using multiple robots. And when they're done, they get an architectural carbon fiber structure, just done with the robots. A lot of their work is really great. So now everybody's getting into 3D printing. Like I said, it's so hyped, even Autodesk decided to get into 3D printing. So last week we actually announced an Autodesk 3D printer on our project Spark. And this is a photopolymer printer. It's printing with a resolution of about 50 microns. But what was important, and it goes back to what I said about how I think 3D printing will move forward in the world through experimentation and new discovery and new invention. What we decided to do with it is to make Project Spark this platform of software available to other 3D printer manufacturers. The printer itself will be open, and we will share the designs freely with anyone who wants it. And the machine we sell ourselves will accept any kind of materials. So you'll have a 3D printer that has open software, open hardware, and open materials. Let me move on. This is like my Ginsu knife slide, but there's more. Okay, what else is going on? One of the things I think is really interesting is the printing of DNA. And so there's a company south of market, it's called Cambrian Genomics, and they're 3D printing DNA. So while in many of the other 3D printers, we're putting in PLA filament or plastic pellets or metal, what goes into their 3D printer is A, T, C, and G. And out the end come strands of DNA. And so why is this important? One, it's one of the most novel uses of 3D printing that I've seen, but I think it lays the groundwork for doing even more interesting stuff. So here's some work that we've been working with a group at the Wyss Institute at Harvard. opens up and delivers a payload of chemicals. So this is an incredible thing. We're now doing things at the nano scale, and we're building machinery that can operate inside of our body. Now, this is just using DNA as a structural component, but not information. If you move on to this idea of using it for information, this is a photograph of a Petri dish, and this is some work done by my colleague Andrew Hessel. Andrew spoke here yesterday, and what they were able to do was to boot up a virus from a text file. So they specified the DNA sequences, they made a bacteriophage, they injected it into E. coli, and it attacked the E. coli. And what you can see are the dead E. coli cells. There was no breakthrough in science in doing this. Another team had done this before. What I found astounding about it is that what it took in order to do that was a smart guy like Andrew, but 14 days, in a mail order account to order DNA, and $1,000. The age of synthetic biology for manufacturing things is right in front of us. Now, many people think that biological manufacturing is a crazy idea. You know, you're going to grow stuff to manufacture it. I don't think it's crazy at all. If you think about it, there are literally billions and billions of factories around us all the time. They're called cells. And we can program them. We program them with DNA. And the results are fairly predictable. I mean, if you just take this example, you go, if I start with a seed, and I add water, and I add soil and nutrients, and I add sunshine, what comes out the other side is pretty predictable. And so I think the future is many of the things that we make will actually be manufactured biologically. It's a new way. It's raw materials. It's organic, obviously. It uses materials. It's infinitely recyclable. It's good ecologically, and we understand it. And so I think there's a new era of biological manufacturing that's on the horizon. So let me move from hardware into the software side. Let me start with this slightly provocative claim that I think yesterday's software tools are failing today's engineers. And what I mean by that is not that the tools are bad, but I think they were built and designed for a different world. Many of the CAD and CAM tools we all use to make stuff were designed for aerospace and defense companies. They were intended to run on mainframes and big workstations. The teams were assembled in an economic structure that was completely different than what we see going on in the proliferation of hardware startups and new companies doing great product development. So a couple of years ago, we kind of stepped back from that and said, where do we see computing going? What is the new platform? What does the new infrastructure look like? And there were two things that came up in our minds about what the future looks like in terms of how do you build software and how do you use it. So the idea that I want to start with is one that I call infinite computing. The idea that computing is getting so cheap that we can have as much computing as we want. And if you truly believe you have as much computing power as you want, how would you change how you design and engineer things? Now, for most of my life, we've treated computing as a scarce resource. You know, it was something to be shared, it was something to be saved, you know, it was precious. But if you were to look around this room, almost every one of you today has a computer in your pocket that's 100,000 times more powerful than the flight computer on the space shuttle. Computing is getting cheap. And the way it's getting cheap is in a predictable way. Unlike any other asset that we can use for any problem, the only asset I know in the world that's getting cheap and getting cheaper in a predictable fashion is computing. And so the idea is, how would we use more computing to do this? And here's this profound thing that years ago, we could have a single computer, and let's say it had a task, and it took 10,000 seconds to do. It would cost you about $1 if you figured out the total cost of doing that. here's the change. Today, through the elasticity of the cloud, we can now have 10,000 computers working for a second, and it still costs $1. We can change the time frame in which we can deliver the results. So not only do I have more powerful computers, I can deliver the results in orders of magnitude less time. So that's one part of the computing infrastructure that's changing. The second part is the devices we do it on. I was joking about mainframes and workstations, but nowadays those are not the machines we work on. If I look around the room, these are the kinds of computers, the ones in our hands, the ones in our pockets, the ones in the pocketbooks, are the kinds of computers we want to do our work on. So we set out, we built a piece of software called Fusion 360, which was a cloud-based design tool. And the idea was to have a design tool that did form and function and fabrication all in one. We also changed the way, in terms of accessibility, it's priced $25 a month. So completely changing the price point for software like that. One of the other things we did is we said for anyone who's not making money using the software, or is not yet making money, like a startup, the software is free. And so it was part of a wider thing. One of the things that I was really proud of this year at Autodesk that we did is we took all of our products, every professional product we have, and we made every product available to students, teachers, and educational institutions across the world. So everybody has free access to professional tools. And this was part of the same idea of making sure people have the tools to do new, great things. So let's look at this. This is the story of a woman who lost her leg in Iraq. She's an avid sports photographer. And rather than starting with a blank sheet, what we really start with is a scan of data. Take that scan of data, take a shape, conform it in trying to build a prosthetic leg to replace her lost leg. So here you can see the creation of a form that was made to fit over the scanned data, as opposed to sculpting this from scratch. Just wait a second, we can watch the creation of the part. And then, one of the other things I said that's important is not just the form, but it's being able to get the function. The important thing that we need to do in the computer these days is not just describe the form. We want to understand the things we make and how they perform. We want to build a digital prototype of what we're making before we actually make it. Because if anyone's ever made anything, you know that when you're done, if you knew at the beginning of a project what you know at the end, you would have done it differently. So this is how do we better understand the things we make before we actually make them. And so what do you do with the power of the cloud? This, for example, this is a rendering. It's a visualization of the final product. It was done on the cloud. The simulation was done on the cloud. Here's machining the actual parts. The toolpaths were generated using the cloud computing. So it's this interesting intersection of the things that are compute intensive, you can do on the cloud, but you can also deliver things locally. And the most important thing, like in a project like this was a handful of very small companies working together. And so how do you get people to collaborate in the new models and how we're all working together? And so it's always struck me as odd that I know more about my neighbor's kid's soccer game than I do about the projects I'm working on. And so this is a way to bring that kind of social activity, the activity of a project, in front of everybody, and then deliver it on the devices that we all want to use. So you have up-to-date project information, you know about the changes, you can use and review and mark up all the stuff right in front of you. Now let me just pause for a second and say, okay, this is a good front end to what I see as the future, in which we divide what we do on the cloud and what we do locally on our computer devices to understand function and form and fabrication. But a couple of years ago, we really started to believe in this idea of infinite computing and saying, how would I design and engineer things differently if I had all the computing power in the world? Now, one of the things that we did is we started with this idea that many engineering problems are a trade-off. They're a trade-off between several variables. It might be strength and weight and cost. This is an example of a plastic injection mold, in which the things we're interested in here is the mold temperature and the melt temperature and the flow rate. But it's a classical problem. It's a multivariate space that we need to explore. In the old world, the way we would have gone about this is what I liken to the game of Battleship, where an engineer says D3 and the analyst says miss. And then you go back to the drawing board, so to speak, and you say F5 and the analyst says miss. And if you think about it and you truly believe, like I do, that you have infinite computing, what you do instead is you put the computer to work and you have it explore the entire space and have it return to you the optimal or near optimal answer. So, and you can do it cleverly. You can use statistical techniques to find the near optimal answer. So we liked what we found in doing this, and it was a great way, we thought, to solve problems. But we said, rather than what we're doing there, instead of asking a question one at a time, in that battleship metaphor, until we run out of time or money or patience, and then saying good enough, we've now gone to the thing of we can ask 10,000 or 100,000 or 1,000,000 questions at once. But we said there might be a better way, and so what we started to do was this idea of, instead of asking for the answers, we want to specify the outcomes. We want to talk about what the outcomes will be, rather than just propose and dispose, propose and dispose. Instead, you say, what's the outcome? So here's a very simple example. A canonical chair. What does it have to do? It has to hold your butt up. It has to support a certain weight. It can't deflect too much. Need a little back on it. So we described it to the computer. The computer came up with thousands and thousands of designs. Here's where you can see it, 3 different models. First model is the traditional chair, just a solid block. Second chair is humanly modeled lightweighting of that chair. You can see a lattice structure in it. The third is a computer-generated design. You can see the weight and the displacement on each of these. So you have, in the end, you have something that's 70% lighter than the first one, with almost the same amount of deflection generated. And before anyone says, it's not to replace the designer, it's to aid the designer and engineer in finding better answers to the problems. So let's look at a slightly more complicated example. This is a bicycle. Here's a bicycle, same technique applied to it. Describe the space volume that it can fill, describe the loads on it, describe the outcome that you want, and here's the shape. Here's the inside of what that shape looks like. Back to what I said, it's cool that you could do this, but up until recently, I had no idea how I would make something that looks like this. Now go back to what you saw with Joris Larman's work with the robotic welder, or the Mori Seiki of the welding followed by machining. And all of a sudden, I start having an idea that I could actually manufacture some of this. And here's what the final bicycle looks like. Okay, here's another one done by the identical technique that we used for the chair and the bicycle. This is a heat exchanger. So this is a heat exchanger in which no individual modeled the geometry. What we talked about is the outcome we wanted in terms of engineering performance, and the computer generated the model for this. It generated thousands of models, and this is the one that the designer finally chose. And here's one last example I want to show you. This is some work that we did with Airbus, and this was work imagining the aircraft of the future, imagining the plane of the future. Look at the outside. I think it looks awesome from the outside. And what you can see is that this is often true. Things are made out of uniform materials, but the stresses placed on them are not uniform. Many of the techniques I talked about in the new way of making things allows us to create materials and forms that are unique to the thing we're making, rather than taking off-the-shelf materials. We can place material at any point in space. And so if you see here, you can really see what happened. We removed material where it was not really needed, and added material in the places where it was really required. So what you get is an airplane that's awesome on the outside, and I think it's even cooler from the inside. So, what I talked about this morning is a little bit what's going on with hardware, what's going on with software, and how I see the future evolving. And I hope you agree with me that, together we are radically changing the way we design and make things. Thank you.